Bismillahirrahmanirrahim. In the last lecture, we were discussing improper integral of second kind. So let's continue improper integral of second kind. Uh, I was explaining this real line. Let's now again this real line. Remember, in integral a to b f of x dx, we never be less than a, and we never be greater than b. This means we can move towards a only from right hand side because we never be less than a, and whenever we move any number from right hand side we write a positive. Similarly, uh, on the number b we always move only from left hand side because we never be greater than b. So in that case we write b negative. So remember, on lower limit we always write a positive because we can move from right hand side, and upper limit we write b negative because we move only from left hand side. But any number c between a and b, we can move from both sides, either from left hand side or right hand side. If we move toward c from left hand side we write c negative, and if we move from right hand side we write c positive. So if you understand all these geometry, so let's come to the improper integral of second kind. So suppose if we have improper integral of second kind and first type. What does it mean first type? First type mean the function f of x is infinity at the lower limit a. The example of such a function is this: f of x is equal to 1 over x minus a, and when we put x equal to a, the function became infinity. So second kind and first limit, how we solve this integral? We solve this integral simply like this: limit, we write limit t tends to a positive and t to b f of x dx, and then what we have to do, just integrate this integral, and at the end put t is equals to a. Put t is equal to a positive mean we move towards a only from right hand side. Similarly, if we have improper integral of second kind and second type mean the function f of x is infinity on upper limit. The example of such type of function is 1 over x minus b. You may ask, why I write x minus b, why not b minus x? Because we are discussing only those integral where integrand or function is positive. So if I write b minus x, then this function may be negative because b is upper limit. So I write x minus b so that our function always positive. So remember, we are discussing only those integral where function is positive. So in that case, when we have second kind and second type, we can write such integral in this way: limit t tends to b negative a to t f of x dx, and evaluate this integral, and at the end put t is equal to b. Similarly, improper integral of second kind and third type where function f of x is infinity between a and b, any number c. So in that case, and the example of such type of function f of x is equal to 1 over x minus c. An example of function you see here, and in that case when f of x is infinity between a and b, any number c, we can break this integral at that number, and we write in this way: a to c f of x dx and c to b f of x dx. So break, first of all we break integral in two parts, and then because this function f of x here on upper part is infinity, so this means this is second type, because in second type you see function is infinity on upper limit. So we write limit t tends to c negative because function is infinity on upper limit. So we write limit t tends to c negative a to t f of x dx, and because function f of x is infinity here on lower limit, so we write limit t tends to c positive t to b f of x dx. So actually when we break f of this integral a to c, c to b, the first one is second type and second one is first type, and according we write whenever we have upper limit we write negative, and whenever we have in function infinity at lower limit we write c positive, and we can evaluate these two integrals separately. If any one is divergent, then this complete integral, third type integral, is divergent. Of course there are other mixed type of integral which are mixed from first improper integral of first kind and in a second kind. So we will discuss some mixed type integral also in the example. Let's solve some example related to first kind, second kind, and mixed kind. So we have to evaluate this improper integral. This is improper integral of first kind. Why this is first kind? Because upper limit is infinity, and the type is second type because upper limit is infinity. So we can write this improper integral in this way: limit t tends to infinity 1 to t dx over x square, and then we integrate 1 over x square, we get minus 1 over x 1 to t, and then I put these limit, we get this term. And remember, when we put limit t tends to infinity, 1 over t is 0, and we get answer is 1. Hence the integral is convergent and convergent to 1. So this improper integral is convergent. Next we see we have to evaluate this improper integral where a is greater than 0. So what is the kind of this integral? This is first kind, and because the lower limit is infinity, so this is first kind and first type improper integral, and we can write according to above definition this integral in this way: limit t tends to minus infinity t to 0 e power ax dx, and then we just evaluate this e power x, we get e power ax over a, and limit is limit t to 0, and then I put 0 and t limit, we get this limit. Remember, e power minus infinity, remember e power minus infinity is 0. Why? Because e power minus infinity mean 1 over e positive infinity, and e positive infinity is equals to infinity, and 1 over infinity is 0. So e power minus infinity is 0 using this fact here, and remember a is greater than 0. So this term is 0, this term is 0, and we get answer 1 over a. Hence the given integral is convergent and convergent to 1 over a. This is another example number 3, and this is first kind. Why first kind? Because the range because the lower and upper both limits are infinity, so this is first kind, and because both lower and upper limits are infinity, so this is third type. So we can say that this is first kind and third type limit, and this integral according to the above definition we can write in two way, but the first way is easy, so we can write this integral in this way: limit t tends to infinity minus t to t, and for the purpose of integrating I multiply by 2 and 2, and then just I integrate this result, we get this expression, and then I put lower and upper limit t and minus t, we get this expression, and then I put t tends to infinity, first one is also 0, second one is also 0. No, before applying limit, these two expressions are cancelled out. So these two expressions are cancelled out, and we get answer is 0. And when we apply limit t tends to infinity on 0, we get answer is 0. So the given integral is convergent and convergent to 0. This is another example we have to evaluate, and it is very clear that it is first kind and third type. Why third type? Because both lower and upper limits are infinity, and we can write this first kind and third type improper integral in this way: limit t tends to infinity minus t to t. In order to evaluate this improper integral, we write t is equals to we write u is equal to x square, and we get du is equal to 2x dx. Then we get this integral in this way, and then I integrate 1 over u square plus x square, integral is tan inverse u, and then I put limit minus t to t, we get but before applying limit minus t to t, remember minus t to t limits are for x, not for u. So before putting limit we must convert u into x, so instead of u I put again x square, so we get this expression, and then I put minus t to t limit. And again, before applying limit, both these two expression are cancel out, and applying limit on the zero, we get answer is zero. So given integral again is convergent and convergent to zero. These are some example. You have to solve these example. These are very simple example. Let discuss example number 6, and this is integral. Now you see neither lower nor upper limits are infinity, so this integral is not first kind. But the function, if we put x is equals to 1 in this function, then integrand or function became infinity, so this means this is second kind. And because the function is infinity on upper limit, so this means this is second kind and second type. And because function is infinity on upper limit, and on upper limit we always write negative, superscript we write negative. So this integral can be written as t tends to 1 negative. 1 negative, why? Because 1 is upper limit, and on upper limit we always write negative. So I write this integral limit t tends to 1 negative 0 to t, and integrate this expression, we get sine inverse x, and then I put limit 0 to t, we get this term, and at the end I put t is equal to 1 and sine inverse 1 is pi by 2. So this integral is convergent and convergent to 1. This is another integral, and you see neither lower nor upper limits are infinity, so this is not first kind. But this function or lower limit, if I put x is equal to -4, is became infinity, so this is second kind and first type. Why first type? Because on the lower limit the function became infinity. So because on lower limit this function is infinity, we can write this integral in this way: limit t tends to -4 and in superscript positive. Remember, on lower limit we always put t tends to positive. Limit t tends to a positive, because on lower limit we can move only from right hand side. So I will write limit t tends to -4, and in superscript positive t tends to 0. And then I integrate this integral in this way. I first also multiply by -2 and 2 in order to complete the integral, and then I integrate this expression, we get this result, and then I put the limit t tends to 0 on this result, we get this result. And finally I put t is equal to minus 4 here. This -4 t square, putting -4 mean 16, and 16 is 0. So finally we get our answer is -4, and this means the given integral is convergent and convergent to -4. Let's see in another example. This is again, but you see this integral, this 1 over x square became infinity at x is equal to 0. So this means this is second kind and third type, and because second kind and third type, we break this integral on the point 0. So I write this integral -1 to 0 and 0 to 1. And because now this is second type and this is third type, so I write limit t tends to 0 negative, because 0 here in upper limit, and here I write limit t tends to 0 positive, because 0 is here is in lower limit. And then I integrate these two integrals. These are very easily, we get this for first integral, and we get this again for second integral, and then I put the limit, we get these two expression. Before putting limit, remember these term, remember these limits, and limits are these: limit x tends to 0 negative, limit x tends to 0 negative 1 over x is minus infinity, and limit x tends to 0 positive 1 over x is positive infinity. And let's see, these are again on these geometry. I think there is no geometry, so remember this fact, because whenever we move from you see here, whenever we move from left hand side, so when we move in 0 from left hand side, so this means we always negative, and when we move from right hand side, from the 0, this means we always positive. So in that case, when we write x tends to 0 negative, we mean we always less than 0, and we always less than 0 mean we always negative. That's why 1 over x answer is minus infinity. But whenever we write limit x tends to 0 negative 1 over x, in this mean we always greater than 0 but never be equal to 0, but never be equal to 0. So in that case we always positive, and this is the reason that limit x tends to 0 positive 1 over x answer is positive infinity. So using this fact, we get our answer here. You see, limit t tends to 0 negative 1 over t answer is minus infinity, but minus we have another minus here, that's why we have minus minus plus. So we have plus infinity, and this minus 1 is remain same. Similarly 1 over t and 0 positive, we have answer is infinity, and infinity is 2 infinity, minus 1 is minus 2, and 2 into infinity is mean is infinity, and infinity minus 2 mean infinity. And this means this given integral is divergent. So the given integral is divergent, and remember these facts are very important for these result. And x tends to 0 mean x never equal to 0. Remember this fact. X tends to a mean x never equals to a. X tends to a mean x never equal to a. So this is last example related to first kind and second kind in computational way. So this is from lower and upper limit clear that this is first time, but on the other hand you can see if I put x equals to minus 3 in this range, minus infinity to infinity, then this function became infinity. So at the same time this integral is first type and second type, so we can say that this is improper integral of mixed type. And at this time this is third type from first kind, and this is also third type from second type, because minus 3 is in between minus infinity to infinity. So this is actually first kind third type and second kind third type integral. And we can break first of all this integral minus infinity to minus 3 and minus 3 to infinity, and then because with respect to minus infinity this is first kind and first type, we can write t1 tends to minus infinity, and because with respect to upper limit this function became infinity, we can write t2 tends to minus 3 and negative, because minus 3 is upper limit. Similarly here minus 3 is lower limit, so we can write t1 tends to minus 3 positive, because minus 3 here is in lower limit. Similarly on the upper limit we can write t2 tends to infinity, because this is upper this is first kind, just we write t2 tends to infinity. And let's now evaluate these two integrals separately. If any one integral is infinity or divergent, then this given integral is also divergent. To evaluate first term, I write this first term again is, and then I integrate, we get this term, and then I put limit t1 and t2. In this limit we get this result. Let now put t1 tends to minus infinity. When I put t1 tends to minus infinity, this became 1 over infinity and this term is 0. But when I put t2 tends to minus 3 here, minus 3 mean 27 minus 27, and this is 0, and 1 over 0 is infinity, and infinity into minus 1 over 3 is minus infinity. So first one is divergent, so this means no need to calculate the second integral, because first one is divergent, and this means the given integral is also divergent. So our given integral is divergent, and let's suppose if our first limit is convergent, then we have to calculate the second integral. And if second integral is also convergent, then what is the answer of our given integral? The answer is the sum of these two integral. But if second one is first one is convergent and second one is divergent, then our given integral is also divergent. So our given integral is divergent. These are some example. Remember, I believe this chapter we can break in two way. First way is the computational way, and second way is the theoretical way. Up till in example number 9, what we have done, we calculate integral, and after finding integral, if answer is plus minus infinity, we can say that the given integral is divergent. Otherwise, we say the integral is convergent. So after calculating, we can say it is convergent or divergent. But in theoretical part, that is the second part, now start. In second part, instead of calculating the integral, just by using some theorem, we can say that the given integral is convergent or divergent. So let's see what is the second part. So first part, that is the computational work, is complete, and let now start the second part, that I call the theoretical part. And without, in this theoretical part, without calculating the integral, we can say the integral is convergent or divergent. This is the second part of this chapter, which I call the theoretical part. And in this part, we do not calculate the integral, but by using some theorem, actually using three theorem, we can discuss the convergent or divergent of the integral. And the first theorem, and the name of the first theorem is the comparison test. Remember, in comparison we required some standard, because in comparison, first thing that we require is the some standard results. So these are two standard integral from which we can use these two integral to compare in this theorem. So these two integral that you see here, the first one is called the geometric or exponential integral, and second integral is called the p integral. Why we are discussing these two integral? So that we can use these two integral in theorem number 1, and the name of the theorem number 1 is comparison test. And in comparison test we required some standard integral. Remember, in this test we do not use only these two standard integral, but we also use some previous integral that you know from previous knowledge. So first let discuss these two integral, then we discuss these theorem. The first standard integral is called the geometric or exponential integral. You see the integral of this type. And what is type? This is actually a first kind. Why first kind? The upper limit is in infinity, and the type is second type, because the upper limit is infinity. So this is first kind and second type. But this integral is called the exponential integral, and this integral is divergent and t is constant, and this integral is convergent if t greater than 0, and diverges if t less than equal to 0. You can see proof in any advanced calculus book of this theorem. So but at this time I just using result of this integral. So this integral is convergent when t is greater than 0 and divergent when t is less than equal to 0. What you say about this integral? This integral is convergent or divergent? Of course this integral is convergent, because if we compare this integral to this integral, we get t is equal to 1, and t is equal to 1 greater than 0 means this integral is convergent by exponential integral. Similarly, if you compare this integral to this integral, we have t is equal to 2, which is greater than 0, and this means from exponential integral this integral is also convergent. What about this integral that you see many times? What about this integral? If you compare t from this exponential integral, we get t is equal to -1, and t is equal to -1 is infinity, means this integral is divergent. So actually I want to show you another side of this theorem. You see, this is exponential integral. Why this exponential integral is convergent? Because you see the limit of integral, you see a to infinity. A to infinity means we have to cover this integral up to a. For example, if this is a and this is infinity, so we have to cover a to infinity area, and a to infinity is extremely large. We can never think such area. So if your function is increasing function, because you see in this integral this is increasing function, exponential, and the graph of exponential function is like this. You see This is the graph of exponential integral. And when you have to cover the area between a to infinity mean you have to cover up to infinity area. So whenever your function is increasing function between the limits a to infinity, then your such type of integral is divergent. So whenever your function is infinity between a to infinity or 1 to infinity, then it is quite possible that integral is divergent. This is the reason that you see in exponential integral e power minus tx. This is decreasing function. So whenever you have a decreasing function between the limits a to infinity, it is quite possible that it is convergent because the function is decreasing. But if your function is increasing function like this, you see here this e power x, this is e power x is always positive function, it is increasing function, then integration of this function from 1 to infinity is divergent. So this integral is convergent only when t is greater than 0. The second integral that we use as a standard integral is the p integral, and the p integral is defined as a to infinity dx over xp, where p is constant and a is greater than 0. A should be greater than 0, and this integral is convergent if p greater than 1. Remember here p is greater than 1 and divergence if p less than equal to 0. So if the p integral is convergent if p greater than 0 and less than equals to 1. This integral is divergent. Let's see these example. If you compare these two examples, we get p is equal to 2 and 2 is greater than 1 mean this integral is convergent from p integral. And you see if you compare this integral to p integral, we get p is equal to 2.5 which is greater than 1, and this means this integral is divergent. What you say this integral, if we have this integral, for example, if we have 2 to infinity and x dx, this integral is convergent and divergent. So if we compare this integral to this standard p integral, we have p here, p is minus 1, so p is equals to minus 1. This means this integral is divergent. Again, with respect to geometric point of view, this integral is divergent. Why? Because this x is increasing function. This x is increasing function, and when we integrate it from 2 to infinity, then we get the very large area. That's why because the definite integral mean area under the curve. So and x is increasing function. So between 0 to infinity, from 2 to infinity, for example, if we have 2 here, 2 to infinity, this is x is equal to 1. This is the graph of linear function. The area under this curve is very large, and this is the reason that this is divergent. So this integral is divergent from p integral. So these are two standard integral, exponential integral and p integral. Let's now discuss three theorem for the convergent or divergent of improper integral of first kind. So the name of the first theorem is the comparison test, and in comparison test we have two parts. First part, whether you have to check it is convergent or divergent. So remember, whenever you have to check the convergent, then bring greater function and make the greater integral. So I repeat, in comparison test you have two parts. Either you have to check convergent or divergent, and whenever you have to check convergent, bring the greater function, and in divergent bring the smaller function and smaller integral. So suppose you have to check this integral a to infinity f of x dx, whether this is convergent or divergent, and suppose you decide you prove this integral to be convergent. So bring the greater function, and let's you bring this greater function g of x, and this g of x is greater than f of x. You see f of x is greater than 0 and g of x is greater than f of x, and then make this same integral on g of x as f of x. And what what is the integral on f of x a to infinity? So I bring the same integral on g of x as f of x, a to infinity g of x, and because g of x is greater function, so its integral, this integral is also greater integral from this given integral. And what will happen, let I see you in this way. You see, this integral we have to check whether it is convergent or divergent, and you decide, you can prove it is convergent. So whenever you have to check the convergent, bring the greater function g of x from f of x. So I bring g of x because g of x is greater function from f of x, and then I bring the same integral as f of x. So you see, I bring the same integral, and because g of x is greater function, so its integral is also greater integral, but by some standard integral like p integral, exponential integral, or some other integral that you know from previous knowledge. You know this greater integral is convergent. Because this greater integral is convergent, this means the smaller integral is also convergent. So this also integral is also convergent because the integral of greater function is also convergent. Similarly, if you have to check, if you decide this integral to prove as a divergent, so when you decide to prove this integral is divergent, then bring smaller function. I write for divergent, bring smaller function, and let at this time g of x is a smaller function from g of x, and then bring the same integral on g of x as f of x. And what we get this integral. And because at this time, because we are checking divergent, g of x is a smaller function, this means this integral is also smaller from the given integral, and by some p integral, exponential integral, and some previous knowledge, we know this integral is divergent. This integral is divergent. So because this integral is a smaller integral from the given integral, and this is divergent, this means the given integral is also divergent. So remember, whenever you have to prove the convergent, bring the greater function, and greater function का greater integral भी अगर convergent हो जाए तो इसका मतलब है given function जो कि smaller function है और उसका integral भी smaller है, वो भी convergent हो जाएगा. और अगर आपने डाइवर्जेंट चेक करना है तो स्मॉलर फंक्शन लाएं और उसका सेम इंटीग्रल लाएं, और अगर वो स्मॉलर फंक्शन का स्मॉलर इंटीग्रल बाय प्रीवियस नॉलेज पी इंटीग्रल, exponential integral or some other knowledge is divergent, so उससे greater function जो होगा उसका integral भी diverge हो जाएगा. Now another question is that how to make this greater or smaller function. The answer is that there is no hard and fast rule to make these greater or smaller function, but you know by some your previous knowledge, your intuition, your expertise, you have to make this function. Otherwise there is no hard and fast rule. We will discuss in the next some example how to make these some greater or smaller function, but there is no hard and faster way to make these function. So let's come to the lecture. So remember, whenever you have to check the convergent, bring the greater function, and whenever greater function and greater integral, and if greater function का greater integral convergent है तो definitely smaller function का smaller integral तो convergent हो गई. इसी तरह से अगर आपने divergent check करना है तो smaller function लाए. You see g of x is smaller at this time, and smaller function का smaller integral, this integral is divergent, तो यकीनन greater function का greater इंटीग्रल भी डाइवर्ज हो जाएगा. लेट्स सी एग्जांपल नंबर 1. we have to check whether this integral is convergent or divergent. Then we know so first I decide that I prove this integral is convergent. Why convergent? Because ex is always positive function, and reciprocal or positive function mean negative function, and when you negative or decreasing function, and when you integrate 0 to infinity of decreasing function means it may be convergent. So I decide I will prove this integral to be convergent. So for convergent, I have to make greater function. To make greater function, I do this. We know that ex is less than ex plus 1. Why? Because ex is always positive function, and positive function plus 1 unit is definitely greater than ex for all x greater than equal to 0. And why I write here 0? Why I not write 1, 2, 3 or a? Because the lower limit is 0. So with respect to lower limit, we can write x greater than equal to 0. If our lower limit is 1, I write here 1. If I have 2, then I 2 here. So and then I divide both these two expressions. We get 1 over ex plus 1 is less than 1 over ex. So 1 over ex plus 1 is less than 1 over ex, and 1 over ex can be written as e power minus x. What does it mean? This means e power minus x is greater than 1 over ex plus 1. But what is 1 over ex plus 1? This is our given function. 1 over ex plus 1 is our given function. So we are able to make a greater function from a given function. And what is our greater function? Is e power minus x. E power minus x is greater function from this given function. And then I make this same integral as given integral of this greater function 0 to infinity e power minus x dx. But what is this integral? This integral is actually exponential integral with a is equal to 0 and t is equal to 1. And from exponential integral, we know that when t is greater than 0, this exponential integral is convergent. But e power minus x is greater function, and this integral is greater integral from the given इंटीग्रल. एंड दिस मीन कि जब आपका ग्रेटर फंक्शन का ग्रेटर इंटीग्रल कन्वर्जेंट है तो स्मॉलर फंक्शन का स्मॉलर इंटीग्रल भी कन्वर्जेंट होगा. सो वी प्रूव दैट द गिवन इंटीग्रल इज कन्वर्जेंट. Let's now solve example number 2 where we have to check whether this given integral is convergent and divergent. And by intuition, by expertise and by experience, I decide to check this integral as a divergent. So for divergent, we have to make a smaller function. And how to make this smaller function? We know that log x is less than x for x greater than or equal to 2. Greater than or equal to 2 mean the last point x is infinity. Actually the range of x is greater than or equal to 2 and less than infinity. So remember, and why I write 2? Because the lower limit is 2. Because the lower limit is 2. So x is greater than or equal to 2 I write. And why I know log x is less than x? Because the purpose of log x is to short the number. So because that by log 10, what is log 10 of 10? Log 10 of 10, if I write here log 10, log 10 of 10 is equal to that 1. So log 10, log of base 10 of 10 is 1. So it short the number. Instead of 10 we can write 1. So remember, the purpose of logarithm is to short the number. And this is the reason that we know that ln x is less than x for all x greater than equals to 2 up to infinity. And then what I do here, I just divide these two expressions. We get 1 over x is less than 1 over ln x. But what is ln x? Ln x is given function. Ln x is given function, and 1 over x is less than from ln 1 over ln x means we are able to make a smaller function from given function. And what is our smaller function? Is 1 over x. So 1 over x is a smaller function from given function 1 over ln x, and I make the same integral as the given integral of 1 over x. So we get this integral 2 to infinity dx over x. But what is this integral? This is p integral with p is equals to 1 and a is equals to 2. So whenever p is equal or less than 1, then this p integral is divergent. So we prove that कि स्मॉलर फंक्शन का ये जो इंटीग्रल है ये भी स्मॉलर होगा, ये डाइवर्जेंट है बिकॉज दिस फंक्शन इज स्मॉलर एंड इट्स इंटीग्रल इज ऑल्सो smaller. But this is p integral with p is equals to 1, and this p is equals to 1 and less than equals to 1. This means this integral is divergent, and because smaller function have smaller integral and this is divergent, this means the given integral which is greater integral from this integral is also divergent. So from comparison test, this is also divergent. So these are two examples related to comparison test, and this may be little difficult because there is no hard and faster way to make a smaller or greater function, but we solve two example and you can make some intuition how to build or create a smaller and greater function. And this is theorem number 2, and this is easy to check whether the given integral is convergent or divergent. So let's suppose we have to check this integral, whether this integral is convergent or divergent. So what we have to do, just consider f of x and multiply it by x raised to the power p, and after multiplication by x raised to the power p, apply limit x tends to infinity on this expression. Apply limit x tends to infinity on this expression, and suppose the limit of this expression is equals to L, and then check whether P and L and decide whether it is convergent or divergent. So if P is greater than 1 and L is finite, if P is greater than 1 and L is finite, then this integral is convergent. But if P is less than equals to 1 and L not equal to 0, L may be infinite. L in this case infinite भी हो सकता है, but L must not be equal to 0. So in that case, when P is less than equals to 1 and L not equal to 0, L may be infinite. This integral is divergent. You may ask what will happen when L is equal to 0. In that case, when L is equal to 0, this theorem is failed. So this theorem is only available with respect to second part. When P is less than 1 and L is equal to 0, this theorem is failed. So I repeat, what does it mean by this theorem? Suppose you have to check this function, this integral, whether it is convergent or divergent. Just multiply f of x by x raised to the power p and apply a limit on this expression, and suppose the answer is L. If p is greater than 1 and L is finite, then this integral is convergent, and if p is less than equals to 1 and L not equal to 0, then this integral is divergent. You may ask how we know which power of x power p we have to multiply f of x. This power of x we decide by making the same numerator and denominator power same. We have to, हमें न्यूमरेटर और डिनोमिनेटर में जो f of x होता है उसकी पावर को सेम बनाना होता है, उससे हम x की पावर p को पता चल जाता है कि किससे हमें मल्टीप्लाई करना है. हम इससे रिलेटेड सम एग्जांपल करते हैं तो आपको क्लियर हो जाएगा.